Not to freak you out, but from a geometry perspective, everything around you is kind of wonky. Everything in the world around us is at some kind of an angle. Things like rooftops contain lots of angles, and collections of objects, like GPS navigation satellites orbiting Earth, are arranged based on angles. Relative to some direction, everything we see is at an angle. So, no surprise, geometry has a whole set of tools for making use of all these angles everywhere. Trigonometry. What's more, as the last couple of episodes have shown us, in geometry, our old friend the triangle often plays a big role, and trigonometry is no exception. Specifically, right triangles give us a window into the world of angles and how we can solve problems with them. I'm Jason Guglielmo, and this is Study Hall Real World College Math. When we first introduced triangles, we talked about how the very shape of a triangle is determined by its three angles. And we've talked about how right triangles are a special type of triangle that contain a 90-degree angle. But there's an even more specific relationship between angles and right triangles. Let's consider an angle between two lines. If we add another line that forms a right angle somewhere, we can join up all the lines to get a right triangle. Now imagine we move that new line away from the angle. We obviously get a larger triangle. But no matter where we put that line, the interior angles stay the same. That makes these similar triangles like we talked about a few episodes ago. No matter how big we make the new triangle, the interior angles stay the same. And more importantly, the proportions between each of the sides will be the same. So if that vertical line is twice as long as the horizontal line in our first triangle, no matter how big we make the new triangle, that relationship will still always be true. That means this first angle we set at the beginning decided all of the proportions of the right triangle we made. In other words, every angle has its own unique series of right triangles. As long as you know this starting angle, you can know how big all of the sides should be in relation to each other. And if you also know the actual length of one of the sides, you can figure out the lengths of the other sides based on their proportions. When we worked with similar triangles, we found these proportions by comparing the lengths of sides, but now we'll work out how to find them based on the angle we start with, which is the heart of trigonometry. Trigonometry, or trig as it's sometimes called, uses three mathematical functions to describe the relationship between an angle in a right triangle and the proportions of its sides. To explore how, let's focus on a particular triangle with the side lengths 5, 12, and 13, and look at an angle that isn't the right angle. To hold its place, we'll use the usual math label for naming an angle, which is the Greek letter theta. The three sides of our triangle have certain names based on their relationship to theta. There's the side next to it, called the adjacent side, the side which doesn't touch the angle, called the opposite side, and our good friend the hypotenuse, which is always opposite the 90-degree angle. Trigonometric functions always involve two of these sides and can tell us the proportion between them based on any angle other than the right angle. The first is the sine function, which we write as sin. The sine of an angle is defined as a ratio of the length of the side opposite the angle over the hypotenuse. In our case, the sine of theta is the length of the opposite side divided by the length of the hypotenuse, which neatly comes out to 5 over 13. Then there's the cosine function, which we write as cos. The cosine of an angle is similar to the sine, only it's the adjacent side over the hypotenuse. For our example, the cosine of theta would be 12 over 13. Finally, there's the tangent, written as tan. The tangent of the angle is the ratio of the opposite side to the adjacent. And in this case, that ratio is 5 over 12. These equations all tell a similar story. Namely, that trig functions of angles are just ratios of two particular side lengths. Remember our mini exploration at the start. Basically, that starting angle controls a lot about the possible side lengths and how they relate to each other. That means if we know the length of one side, one of the smaller angles, and a way of calculating trig functions, we can get the length of the remaining side with a little bit of algebra. And if you're wondering how to actually calculate these trig functions, don't worry. As long as you understand the relationship you're dealing with, we usually use a calculator to get the actual answers. That was a lot to take in. But the key is to identify what pieces you have and what you need. Say you want to find the hypotenuse, but only have an angle and its adjacent side. All you need to do is look at our handy three equations and find the one that uses the hypotenuse and adjacent, which turns out to be cosine. To see it in practice though, let's head back to Anne from last episode, who we left at her campsite next to a river. With her water stores refilled, Anne reckons the mountain directly ahead of her would make for an excellent hike. Knowing her own fitness, she figures she could probably conquer the summit and make it back down by sunset if the peak is less than a kilometer high. She sees that the peak is about 2 kilometers away on her map, but it doesn't say how tall the mountain is. Thankfully, her compass has a clinometer, which is a tool that lets her measure the angle of elevation in the direction she looks at. Looking in the direction of the peak, she sees it's 25 degrees above the horizon. Looking at the entire situation from the side, we can see a line from Anne's location at the base up to the peak, and another line from her to the center of the mountain on ground level, the way the map marks it. Connect those two lines and we have ourselves a right triangle. In terms of what we know, we have one of the angles of this triangle and the length of the adjacent side. But what we want to know is the length of the opposite side, which represents the height of the mountain. So we have three ingredients: an angle, an opposite, and an adjacent. Now we get to the heart of trigonometry, finding the right function for the problem at hand. Going back to the definition of our trig functions, there's only one that involves both the opposite and adjacent sides of a triangle: the tangent function. If we call the height of the mountain we're after x in true mathematician style, we can write out this problem as the tangent of 25 degrees equals x divided by 2 kilometers. If we solve for x, we get that the height of our mountain is 2 kilometers times the tangent of 25 degrees. So by punching that into a calculator, we get about 933 meters, which Anne reckons is a perfect hill to finish her day with. So far, we've looked at calculating the lengths of a triangle when we know the angle. But what if the angle is the missing piece we're after? After all, the trig functions tell us that the angle in a right triangle corresponds to the proportions of two sides. So if we know the ratio of two sides, it seems like there should be a way of getting the angle. And there is. Let's look at our expression for any trig function, say the cosine. To solve for the angle, we take the inverse function of both sides. That sounds a little complex, but all it means is we need a new function that does the opposite of the cosine, which we denote with a power to the -1. Now, we ought to be clear, this does not actually mean we're taking the negative power of anything. That -1 is just there to tell you that it's an inverse function. And once again, you'll find the inverse functions on your calculator, usually next to the regular ones. The idea is that if we apply this function, it undoes the cosine function, and we get back the original angle. So when we use that inverse cosine on both sides of the equation, that leaves us with theta equals the inverse cosine of the adjacent side divided by the hypotenuse. All you have to do is plug in the side lengths, use the inverse function, and you're set. To see how these new functions shake out in practice, let's consider Abwaji, a hiker on the other side of Anne's mountain. He's not too far from the base of the mountain and is kitted out with a map like Anne's, only his map also indicates the heights of the mountains in the area. But he doesn't have a fancy compass like Anne has to calculate the slope of the mountain. Abwaji loves the idea of hiking up and pitching his tent on this side of the mountain, so he can wake up the next day to a beautiful sunrise. But he also knows from experience that pitching a tent on anything steeper than about 30 degrees makes for a pretty uncomfortable night's sleep. Looking at his side of the mountain, he can see the ascent is pretty even. From his map, he can simply read off the height of the peak which Anne had to calculate. And the distance from the base to the top of his side is 1.5 kilometers. Much like Anne, Abwaji identifies the two sides of the right triangle relevant to his problem, the opposite and the adjacent side, so he knows the tangent function will be involved. Only what he's actually after is the angle. So all he has to do is arrange the tangent function to take the inverse tangent of the opposite over the adjacent. Plugging in the numbers, it comes out to about 31.9 degrees. Which unfortunately is probably too steep to comfortably set up camp on, or else he risks rolling all the way to the bottom. So he decides to hike over to a less dramatic hill nearby with a flat top to perch on. In general, whether you're calculating lengths or angles of right triangles, the trick in trigonometry is identifying which two sides are involved in a problem and then finding the relevant function. You might still be wondering where we actually get the values these trig functions give us. One way of thinking about it is when we take the sine of an angle, we aren't really doing anything to it. It's less calculating and more looking up the value. The sine of 30 degrees will always be 0.5. That never changes. In fact, if you were doing trig problems before calculators, you'd have a handy sheet that gave you the sine, cosine, and tangent for any angle from 0 to 90. But how do we know that the sine of 30 degrees is 0.5? Well, mathematicians have worked out ways to precisely calculate trig functions, which involve a bit of calculus, an infinite series of calculations, and somehow pi comes along for the ride. On a less theoretical level, though, it turns out we originally derived trig functions by using circles and applying a lot of the geometry concepts we've learned through the past few episodes. Like we've said, geometry and math in general is all about combining what we already know and using logic to solve new problems. In fact, throughout this series, we've seen how the tools of math can describe and help us understand the world around us. Like we mentioned in our very first episode, in many ways, math is a sort of language for describing relationships between different things. Over these last 30 episodes, we've picked up some of the basic vocabulary and grammar associated with the language of math to express ideas and use logic to reason about the world, from combinations to compound interest to the wonderful world of trig. But like any language, the real mastery comes from using it. We hope that with the ideas and tools we've explored, you'll have the confidence to put math into action, pick up new ideas that build on the ones we've introduced, and appreciate all the ways that math really does shape our lives. This has been Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video, give us a like and subscribe. You can learn more about ASU in the videos produced by Crash Course in the links in the description. Thanks for watching.